Hi, it's Nick from Building Point Australia, and welcome to this StatiCa presentation on a beam to column bolted moment end plate connection where the column has flange doubler plates. And here's the connection I'll use to illustrate a way of going about this. So first of all, just to describe the setup, if I hover over something, we see on the bottom left some details. So this beam is a 460 UB82 hot rolled section grade 300. The column is a 530 UB82, and the plate items, the end plate is grade 250, 32 millimeters thickness, and the stiffeners through the column are plate grade 250, 12 millimeters in thickness. And we can see some design moments and shears and so on, design actions coming into the members into this connection. We see the wireframe view and the nodal view. We can select the load case and the members of interest to see further details of these design actions and the bending moment in particular coming in on each member if we select it. So we have a fairly significant setup of design actions in terms of the section capacities, but they should be able to take them. The question is whether the connection is satisfactory and passes the various design checks. So we'll set this going to see how things look in StatiCa. And we can see the software iterating at different load levels here. So it's taking a bit longer than usual for a relatively simple connection, just one load combination. And this indicates that there's perhaps excessive plastic strain. The software is taking a while to come to a final equilibrium situation. And clearly now, looking at the overall check view, we have a number of failures and very substantial failures in this connection. So the plastic strain somewhere is just over 76%. That's far too high for steel, and the design limit is 5%. And bolts, a very high utilization factor, and welds have also failed. And we get a good idea where some problems are from this overall view, but let's go and look at this in more detail. So we go to the check view, we can select a range of options. So the von Mises stress, that's the so-called equivalent stress, turning on mesh and deformation, and I'll bring that down to the minimum scale I can select of 1. And we see very high stresses in the column flange. And if I select the plastic strain view, similarly, high plastic strain, I select that item, it takes me to the correct tab and highlights the item I've selected. And we can see that the plastic strain maximum in this item is the 76%. That is the maximum in this connection. We see a bit more detail of that in this view here. And we could compare these plastic strains to the chart here. So around the bolt holes, clearly we have some very high plastic strain. We really need to be right down here, no greater than 5%. And we could also have a look at bolt forces and contact stresses. And we see some very substantial contact stresses close to these bolt holes. And this will be adding directly to the tension force in the bolts. And for an M24 grade 8.8, that's what we have here, the design tension capacity is 234 kilonewtons. So 437 kilonewtons is clearly very excessive. If we select that arrow, again, we can go to these different details and we see the design tension of 437 kilonewtons there. A little bit of shear is carried by that bolt as well. And the utilization factor for tension is 186%, plus a bit of shear. The squared interaction takes us well over the design limit of 100% utilization. So clearly we've got significant issues structurally in this connection at the moment, despite understanding that the sections themselves and the members can carry these forces. The connection I've got set up at the moment is clearly not suitable. It's inadequate for conveying these forces. So I do intend to stiffen this column flange, but just to give myself an idea of whether a thicker flanged member would work, I'll set that up. So if I go to the Materials tab, we'll see that I've previously set up a 530 UB custom section. The depth and width and web thickness are all the same, but I've made the flange 30 millimeters thick as opposed to a standard 13.2 millimeter thick 530 UB 82. So the grade is the same. I'll simply select that heavy column that I've set up. If you haven't done it already, you could add a new section, select this custom hot rolled eye section here, put the details on the plate and the steel grade in, and then you're able to select it, of course. And so here we have it. This is, of course, not the final solution. It's just an intermediate test to see if we're on the right track here. And the analysis was very quick. Everything is working. We could go and have a look at the behavior so that we can see if we're satisfied with how it might go if we had local thickening to this extent. So now bumping up the deformation scale, we see some deformation at a scale of 11, but things are working much better. The bolt forces are significantly less and are less than the tension capacity of the bolts. So everything is working, but I haven't carried out the buckling analysis yet, which is of course necessary in the connection. So that gives us some confidence that we may well be on the right track if we locally stiffen, increase the thickness of the column flange. So I'll take that back to the required size, and let's see how we might go about this with some backing plates to the column. Well, one option in the end plate operation, we can add backing plates like that. So you specify the thickness. I've got 16. Currently there's a 10 millimeter offset. Let's look at a plan view from the web. We could make that 0 like that, and we could analyze that now. But currently the stiffener doesn't end at the face of the backing plate. We could cut that. We'll see that a bit later, so I won't do that now. And we could also add some welds around the perimeter of these backing plates. So if we're happy to use a full depth backing plate, and for quite shallow sections that might be quite appropriate, but if the beam is of significant depth, that might be quite a bit of extra welding. Conventionally we would butt weld the inside edge of the backing plate to the web of the column, other welds being fillet welds. And so if this is quite deep, there's not very much load transferred in the central region. It isn't necessarily an economical solution. So let's go about this in a different way. I'll untick the backing plate here. And in fact, I'm going to set it up such that I have bolts coming the other way through the backing plate initially. So I actually want to make this a welded connection for now, and still maintain the butt weld of the beam flanges to the end plate, and 8 millimeter leg fillet welds of the beam web to the end plate, but no bolts at the moment, and the plate itself is not welded to the column. If I selected fillet weld like that, then that would be that option, but I'll turn off the welds because I of course want to use some bolting operations. All right, so there's various ways to set up some plates here and create welds around the perimeter and this sort of thing. Some methods take more operations, perhaps not quite as convenient as others. I found using a plate defined as a stiffening member can save us a few operations. So that's the way I'll go about it here. So I'll start a new operation, which will be a stiffening member. But the member itself is going to be simply a rectangular plate. And the thickness, I want to try 16 millimeter thick backing plates, and I want to make that 208 millimeters wide. That could be fine-tuned later. And Even though this is defined as a stiffening member, it's actually going to be plates each side later on, and not quite the full width. So I'll make that a plate grade 250, which I've already defined in this connection model. So now we see our stiffening member located there at the joint with zero rotation and so forth. So let's just get some of these details right. I want to set this up to be with respect to some other plate in this connection. And yes, I want to use end plate 1 to define the location, but I want to make this a doubler like this, but on the inside, of course. So I don't want welding at this stage. If we are happy to have a fillet weld all the way around, and if we were to sit it on that end plate, we could select that option, but I'm turning off the welds there now. And I'll make this go on the rear like this. And this is the reason I'm using a member defined as a rectangular section. It's because I can introduce an offset here laterally, and this will be the thickness of the column flange. So this is one of the adjustments that we might have to make later. If we change the column size, we'll then have a different column flange thickness. We need to just change the offset in the double plate slightly like this. And just some other details. I want to make this offset in the Y direction 230 millimeters to push it up there. And in terms of the rotation, 90 degrees, and the length is 126 millimeters down and 110 millimeters up to give me just a little bit more distance in case this beam is coming in on a slope. So that's not too bad. It's something like the location of the doubler plates I would like. And the next thing I want to do is set up a cut operation of the member, because this item looks like a plate item. It's a member, the way I've set it up. And I want to cut this stiffening member to the column web like this. And there we have some welds. It's a double-sided fillet weld right now, but I want to make that a single-sided fillet or a butt weld. So just to check this, if this was the result that we saw, we might wonder where the weld is. Well, we can hover over this flange, make sure this window is selected first, hover over the item and press delete, and it disappears from the view. So we can see that the fillet weld has gone to the wrong side there, and we can simply change that. The flange returns, the view resets, and I want to make that only 8 millimeter leg. So typically we would butt weld this. We would use this, and in that case it's easier to see. If we turn the transparent view on, we see this yellow rectangle indicating the joining of the mid thicknesses of the welded elements. But of course in the solid view we can see the weld more easily if it's a fillet like that. So I might try a fillet weld here. We would typically butt weld it, as I say, but I'm going to fillet weld it there. And with this full width member with the shape of a plate, we see that that cut to the web creates a slot. Let's just delete this web and look down, and we see that the plates have in fact been cut each side, and there we have a fillet weld to the web of the column. So let's reset that view. So that's fine. That's looking okay at this stage. And the next thing I'd like to do is set up some bolts to go through this member. So now we set up a custom bolt grid. And it doesn't know what I want to connect just yet. And I want to connect 3 items. So we set up 3 there. And the first thing I want to select is this stiffening member that I've defined here. So when I hover over that, stiffening member 1, bottom flange 2, to have it on this side. So the first item is going to be a member, and it's going to be stiffening member 1, bottom flange 2, like that. So now we see the bolt, and sometimes it's easier to put the transparent view on so we can see where the bolt, if it's on the other side, where it is. And so in terms of positions, I'm going to make that -45 coming down from the top. I left a little bit of extra height to that plate, and then a further 146. So -146 there. So that leaves me 65 millimeters clearance from the top of the flange on the beam side, and then a further 16 millimeters. So it's 130. That's twice 65 plus 16, so 146 between the bolts like that. And in terms of lateral distance, that's going to be 65 millimeters, and it's a negative because to bring it towards me. And so let's have a look at these bolts. The first one is on the stiffening member. The second one must be part of the member. So we select the column bottom flange 1, see on the bottom left. So that selected correctly. And the third item is the end plate. So we see when we have selected the bolt grid operation, all three items in orange, that we have the confirmation that we've got the bolts going through the correct plates. Let's proceed to copy that to the other side. So the easy way, once we've set one item up, is to select copy, and then with the new item we make the adjustments. And so hovering over this SM1 bottom flange 1 and transparent view again, the bolts are probably overlapping on the other side, and let's turn that into a plus and see how we go. And we see those three items in orange again. So the second and third items stayed the same, bottom flange and end plate. It was simply a matter of changing the first plate reference and the distance horizontally, in this case, to achieve the correct setup. So that's looking a bit better. What we might do now is shorten these column stiffeners so that they interact with the doubler plate directly. We, of course, have a clash at the moment, and I've turned the plate and weld clash check off in code setup, but if I turn that back on, we'll see, and particularly if we turn the transparent view on, we see the nodes and we see the red overlap of volumes here. So it's up to you, of course, whether you want to see these details. I'll just turn that off again for now. Back to the solid view. Let's cut the stiffener. So the column horizontal stiffener is a plate. So this is adding a plate, a stiffening plate item. This is cutting a plate item. So we want to cut a plate item, and it's going to be select this stiffener here, and it's going to be cut to this member plate item. So member is correct, and that is SM1 bottom flange 2. And we see we got something. It's put a one-sided fillet weld, a small one on the bottom side only, and I want to make that a double fillet weld like that. So now that we have that one, we can copy it to the other side and simply specify the correct detail. So this is stiffener 1C. Change the first item to that. And the second item is SM1 bottom flange 1. Like that. Okay, so this is looking good. Perhaps what we could do is analyze that at this stage. So let's calculate and see how we go. We would normally put fillet welds around the other three sides of this doubler plate, but let's see how it goes without that. Okay, so that's interesting. I didn't, of course, make a connection at the bottom. Things are closer to working than before, but of course we still have some significant failures, and some of the deformations and other results would be a little bit similar to what we saw before, but not quite as extreme. So let's continue with getting the connection correct, and to create welds around the other three sides, we can use this custom or additional weld operation here. So just like with the bolts, this is a bit more of a detailed type of method of creating welds. A lot of other operations have welds within them, end plates, cleats and stiffeners and so on, but we can add welds in other circumstances in this way. So we do want an edge to a surface weld, And the first item is going to be a member item. Again, this is going to be SM1 bottom flange 2. So we select that. And we want that to be welded to C bottom flange 1. So that's the second item here. C bottom flange 1, like that. And now we see a few numbers showing up, but there again, easier to see if we select the transparent view. And let's bump up that weld to size 8. And index 1 is on that side. We already have a weld there. We don't want that. We could select index 2 to do it at the bottom there. Let's just have a look at that. And there we have it. And nicely with this type of operation, we can add multiple indices when the rest of the details are the same. We just separate them by a space. So index 3 and 4, like that. And we get the welds on the other two sides like that. So as I say, we could have achieved the welds a little bit differently, and if I hadn't welded this side already, I could have welded all 4 sides if I wanted to by including side 1, but I didn't want to put an 8mm fillet on that vertical side against the web. I wanted to, well, not to the flange, I wanted to fillet weld it to the web. All right, and now we want to do the same thing on the other side, so same sort of process. We copy that, and this time this is SM1 bottom flange 1, and we go to the transparent view and we see the indices we want are 1, 2 and 4. So simply a matter of changing that. Let's turn on the solid view to have a look at how this all appears. So I'm fairly happy with things at the top flange now, and of course the idea is to repeat this process at the bottom. But just prior to doing that, I'm going to select calculate to see how this goes, because there's compression, of course, horizontally in the bottom flange into the stiffness, so we expect it to go reasonably well, and even without bolts here. So that's, I think, quite encouraging that things are working fairly hard, but even without any bolts at the bottom to help us take shear, we're getting a satisfactory behavior. So of course we are likely to have some reversal, and we wouldn't leave the connection just like this. We would repeat the same sort of process around the bottom flange to complete the connection. So I won't go through that. It's the same process, just repeating it at the bottom. So here's a different connection where that has been done already, and we see the results. Some of the details or the utilization factors are slightly lower, and I have completed the buckling analysis here. And so that's done. Instead of being on the design menu, have the check menu selected and use the drop down to do the strength analysis plus buckling. And so that means we can review the buckling results as well now. But just having a quick look at some of those regular type behaviors. 1 mi stress with a deformed scale of 10, not too bad. Bolt forces, stressing contacts. We see some contact stress on the end plate at the top there. That would be creating some prying, adding to the bolt tension at the top, but 193, still less than the bolt tension here. I don't think there would be any prying here because there's no contact stress on the end plate itself, but between the doubler plate and the column flange, there is a bit of contact stress just in supporting that substantial tension that's coming in. But all of that's working. Plastic strain, we know it's not above 2.9% in the connection, but we can have a look at that. Let's look at that end plate. And there we have 2.9%, but that's all working. We get a closer look at it there. And finally, we can have a look at the buckling results. And now that we've carried those out, we select the buckling shape here, the buckling tab in the results, and we can select the various buckling modes and look at the buckling load factors as well. So we want everything to be at least 3 or above 3 as a buckling load factor in a connection. But what we see with the first couple, that these are not really modes relating to the connection. All of these buckling load factors are high enough anyway, so nothing to be concerned about. But If your buckling mode is away from the connection, I would say like this, your member checks, your section checks would pick up the issue. If the buckling load factor for a buckle like this was significantly less than 3, it might indicate an issue with the member. But if it passes the AS4100 design checks, then that's fine. So within the connection vicinity, we're looking for at least 3. And so buckling mode 3 has a buckle in the web, so the compression in the column and the significant shear developed in that zone due to the connection. We have a buckling load factor of about 4.5, easily above 3, so no need to stiffen this for slenderness or buckling purposes. So the plastic strain is okay in that zone, and the slenderness or the buckling consideration is okay. So that's a nice, quick and easy way to check those aspects, I think. If you have any questions, or in fact, if you'd like this connection, I could send it through, please let me know at Building Point. Thank you very much.